Hello friends, welcome to the next segment of optical physical properties of under the edges of polymer testing. In the previous segment, we covered about the various thermal properties like heat conductivity and diffusivity, differential scanning calorimetry, thermogrammetric analysis, thermomechanical analysis. Apart from this, we discussed about the optical properties in which the refractive index, reflectrometer, polarization and polarization optical testings, these all things were covered. In this particular segment, we are going to discuss about the other optical properties like non-destructive testing for transparent polymers, transmission, absorption, reflection, gloss, intrinsic, diffuse, reflectance and haze, infrared spectroscopy, color and laser technology. Now, let's talk about the non-destructive testing of transparent polymers. So, between the crossed polarizers, the processing related orientation of polymer molecules appears as black or isoclinics and colored lines and patches. While isoclinics, this provides the comments about the molecule's preferred direction, and isochromatics offer details about the anisotropic circumstances present inside the molded portion. A circular polystyrene device with the center gate is shown in this particular figure and the linear polarized transillumination without any external loads. According to this particular figure and equation, the isochromatics can be used to determine the position of isochromatics and their assignment to a specific color order, starting with the black isochromatics of the zero order. This black cross formed by the isoclinics indicates the symmetrical star-shaped main orientation direction of the molecules. The interference caused by light waves moving through anisotropic plastic causes the color orders to appear. The light rays, they are not separated if there is no anisotropy, and when polarizers are crossed, the darkness predominates and the zero order isochromatic is present. Therefore, retardation does not occur. Specified wavelength in white light are extinguished when anisotropy rises and the remaining light component takes on colored hue. Now, a particular equation can be used to compute the amount of birefringence along the circular center gated flow route as per the figure, and this is delta n is equal to k lambda d, where delta n is birefringence and k is the color order number starting on the outside of this circular disc with always black zero order isochromatics, and lambda is the wavelength of the isochromatic used for the evaluation, d is the thickness, and k and lambda yields the optical retardation. Now, microscopic polarized light testing method for amorphous plastic. Amorphous polymers that aren't filled don't form any structure that can be seen under a light microscope. However, polarization microscopy techniques can be used to find microscopic heterogeneities on variation in anisotropy. Point accurate measuring of retardation in a range from a few nanometer to approximately 80 meter is possible with the employment of tilting plate and rotary compensators. The key benefit of microscopic approaches is that measurement can be performed without the need of isochromatic line gradients across many order in the molded item. Thus, it is conceivable to manage anisotropy variations and differences within extremely small range, is maybe say 4 micrometer, such as the phases of polymer blend on the one hand and film anisotropies with basically constant retardation on the other. Now, if we talk about a semi-crystalline plastic in light of microscope, the spherulitic structures are frequently apparent in semi-crystalline polymers. The spherulities, which are spatially composed of fibrils, can be tested in polarized transillumination to a minimum structure number size of 1 meter by cutting them into semi-thin section, that is section of the thickness of to say 10 meter. Now, this particular figure depicts the spherulitic structure of a polypropylene film made by the crystallization on a liquid immediately from the melt. And due to the production process, holes have been formed at the limits of spherulities. Sample can be extracted from crucial areas of molded part, processed during the procedure, and then examined using the light microscopy. Now, type from form, distribution, size, and a number of occurring phases must all be taken into account in such an evaluation. Now, if the chosen processing conditions can then be inferred from that particular aspect. A typical multi-phase structure of a polypropylene part made from pellets is shown in this particular figure. At the granule borders, different polypropylene modification can be seen, each with the different set of optical and mechanical characteristics. It is necessary to measure the optical data at the spherulities in order to determine these alterations such as birefringence values and optical signs. Let's talk about the transmission, absorption and reflection. Color, transparency, haze and hiding power are examples of optical qualities that primarily depend on two phenomena of incident light. The material absorbs incident light, converting it into heat. Only by measuring the amount of reflection and transmission can this value be calculated. Scattering inside the medium causes incident light to be reflected from its original direction. The spectral transmission. The ratio of transmitted to incident spectral radial flux is known as the spectral transmission, which is spelled out as tau lambda is equal to phi E lambda, constant tau phi E lambda. So, when a light beam with a wavelength of 551 nanometer passes through the test specimen, it loses 30% of its energy as absorption, and the reflection according to the degree of spectral transmission of tau 551 nanometer is equal to 0.7. Now, if we talk about the absorptance lambda, it is defined as the ratio of the incident spectrum radiant flux phi to the total spectral radiant flux absorbed by the medium, which can be represented as A lambda is equal to phi E lambda over phi E lambda. Now, similarly, the spectral reflectance P lambda can be determined as P lambda is equal to phi E lambda P over phi E lambda. Now, this phi E lambda P at constant P is the total spectral flux reflected at the medium interface. This can only happen on one mirror surface or a number of clear media surfaces. Diffuse reflectance is a result of a mirror surface when transmission does not happen, and the luminance of the reflecting surface is compared to the luminance of a perfectly matte white body under equal illumination and observation condition to establish the degree of diffused reflection. Now, spectrophotometers like Minolta CR40, they are used to measure the level of diffused reflectance and transmission. As a result of having little or no absorption in visible light, the majority of unfilled amorphous polymers are transparent, and transmittance is significantly changed by addition of colors and process related additives like heat stabilizer and UV stabilizers, and due to their tiny size, these compounds are typically only detectable by electron microscopy. However, a light microscope can make a comparatively big particle of commonly used black stabilizers, which can be visible. Now, the image allow for conclusions to be made regarding particle agglomeration and distribution. This particular figure illustrates a 2 meter thin segment of a polyethylene matrix of a high tension cable with a nearly unagglomerated, very even carbon black distribution. Let's talk about the gloss, intrinsic, diffuse, reflectance, and haze. The surfaces of technical materials are always a little rough, and due to this, they only partially reflect lights when illuminated directly, as illustrated this particular diagram. Here you see that the directed one, dispersed one, and diffused one. The glass, the size of the surface roughness determines how the reflected light is distributed. The different intensities emerge when the resulting reflection is measured from various observation angles, and glass refers to this particular quality. Haze. The surface haze is the word used to describe the diminished gloss produced by such surface roughness. Let's talk about the intrinsic haze. When light strikes centers that is scattered, this is the light beam and this it's scattered this over the polymer, these are the fillers and these are the certain pigments. So, when the light strikes centers that scatter light like pigment or spherulities on the semi-crystalline polymer, internal diffuse reflection takes place, producing an inherent haze. The combined light reflected by a sample comes from both the surface and the inside. Because of this, the body's pigment help to create the perception of color. Let's talk about the factors on which the gloss generation in polymer and its evaluation depends. The characteristics of the specimen surface, reflection and scattering that are influenced by its structure, roughness, curvature and a plane position. The incoming light is spectral distribution, intensity and geographical distribution. So, observation angle and distance of the observer and the color and transparency of the specimen, as well as the color, brightness and reflection properties of the surrounding of the surface tested. The measurement of dispersed light dispersion yield the gloss height, say h. Now, this can be represented as h is equal to IP over ISW minus IP naught over IS naught. Now, this IP, the photometer current intensity with a specimen applied at alpha 2 is equal to alpha 1, IP naught, this one, with the specimen applied at the perpendicular light direction and alpha 2 is equal to 0, and ISW, this one, with the mat with standard applied and alpha A2 is equal to alpha A1, and this particular is not with the mat wide standard applied at perpendicular light direction and alpha 2 is equal to 0. Now, using the necessary gonio-photometer under the angle alpha 2, photometer current IP is determined. Now, this is the schematic diagram of a gonio-photometer for determining the gloss height. A gloss scale is created using the gloss height and it has a white standard with a gloss of G is equal to 0 and a black standard made of polished black glass with a refractive index of N is equal to 1.57 and a gloss of G is equal to 100. Now, determining the surface roughness by gloss measurement. Gloss value is a good tool for describing these surfaces because it heavily depends on specimen surface roughness. Thus, after test for wear and scratch resistance, this method can be used to evaluate the surfaces. In the sand trickling test, the gloss value G of a polypropylene material with the varied scratch resistance is affected by the amount of sand used as compared to the initial gloss value. Now, determining the surface roughness using interference microscopy. Now, we refer to the overlapping of two coherent light waves as interference. Then, depending on the magnitude of the phase difference, maxima and minima happens. The necessary retardation may be caused by minute height differences on reflective surfaces, inhomogeneities in transparent material, and B refringence in anisotropic phases. In Tolenski interference setup, a very small air wedge is placed between a surface and a semi-transparent mirror in microscope under the monochromatic light of a specific wavelength lambda. Now, this is the typical figure. This surface scratches in the interference image and surface profile with the roughness height R. Now, the interference fringes that result closely match the surface contour. And now, depending on the setup, minimum height difference of 30 nm can be recorded. Now, this demonstrates the interference picture of a scratched polystyrene specimen surface that had been gold coated in a vacuum before measurement to improve contrast, and metal interference filters are used to set a wavelength lambda of the necessary monochromatic light. Now, by tilting the interference mirror, the distance b between the fringes can be altered, which can affect the measurement precision. It is possible to measure that alpha 1 and alpha 2 fringes deflections with a microscope or on a photo. Now, by performing the differential interference contrast under the polarized light, it is possible to achieve very good three-dimensional contrast of slight surface height changes in the microscope. Now, black and white or a color variation or variations are created from a little variation in surface height. When linear polarized light is employed, direction dependence develops, meaning that a linear image patterns are suppressed in the direction that a Wollaston prism splits light. Circularly polarized light entirely eliminates this particular phenomenon. Let us talk about the color. The majority of the plastic is transparent or translucent, making it easy to color with the color of all intensities. The thickness, the quantity and the distribution of the pigment in a final item as well as the processing all affect the color quality. The color of a surface has a significant impact on how it is perceived. Red, green and blue are three primary colors of light. Their intensities are measured separately to determine the color of light. A matte white ball with an internally coated coating provides diffused illumination to the surface. Through the employment of an optical system with an optical wedge, the light that has been diffusely reflected is directed onto a photocell. The intensities obtained, they are assigned to the color red, that is X, green, that is Y, and blue Z. So, the equation which we are going to write, they are used to derive the standard color X and Y from these values, like X is equal to X plus Y plus Z, and Y is equal to X plus Y plus Z. Now, we get the color triangle depicted in this figure by entering the common color values X and Y as the ordinates and respectively in the two-dimensional coordinate system, where the E is the achromatic point of equal intensity spectrum. Now, measurement, precision and reproducibility are strongly influenced by the nature and preparation of a specimen. Now, it is important that the representative object chosen for the measuring be both robust and small. If the specimens exhibits orientations, they lead to dichroism. Now, color is assessed in reflected light when tests are conducted on material that are completely opaque. Now, depending on the background choice, the color registration issues happen when using this technique or translucent specimen. Now, there are two procedures to be used. A color contacting agent is used to register the color value on a smooth white background. On a rough surface, color values are registered without the use of a color contacting agent. When strongly scattering specimens are tested in reflected light mode with a white or a black background, both with and without contact medium, while transparent weakly scattering specimens are measured in transmitted light. So, after being compacted in dishes, the powder, grain or fibers are assessed for their color values. The color values of liquid are measured in cuvettes. The glass covers on solid porous or liquid samples can be problematic, and the amount of the value contamination that result is influenced by the cover material's refractive index, self-absorption, and a glass thickness. The frequently ill-defined optical contact between the sample and cover leads to the further inaccuracies. Then talk about the color determination for filled polymers and polymer blends. The both material science and the plastic engineering concentrates on the following structure factors to test the optical characteristics of filled and reinforced polymers, like orientation of the fillers and reinforcers, filler or fiber distribution and agglomeration, as well as the influence on morphological formation in the matrix, and various methods of light microscopies are utilized. There are numerous light microscopy techniques being used, like this particular figure illustrates the distribution errors of a glass fiber in colored EP resin that were made apparent by polishing against the direction of fiber orientation. You see that the glass fibers, the different type of cavities, and this is the matrix. Now here a combination of a dark field illumination of the microscope and the inherent color of the matrix material is combined to produce effective contrast. Now in experiments those employing the incoming light and the bright field illumination, the real colors of the specimen component cannot be reflected because the spectral makeup of the light changes under the microscope. Now front surface mirrors, they are utilized in the dark field to provide the illumination without a spectral shift. The true specimen color, they are presented in this microscopic image. This demonstrates the variation in color representation using an unscratched polished piece of a recycled sawdust packed polyolefin blend as an example. Now both the pure contrasting method and a way to identify colors can be employed with the tinny lightning. Now this is a polished section of a vertically illuminated sawdust filled polyolefin material. This is the bright field and this is the dark field illumination. Let's talk about the infrared spectroscopy. The infrared spectroscopy is an absorptive spectroscopic technique that uses the wavelength between approximately 780 nanometer to 1 mm. The mid-range infrared spectrum which encompasses wavelength between 2.5 and 2.25 meter is the most crucial one for studying the polymers. The term wave number is used to express the spectral range as the reciprocal of the wavelength is centimeter inverse. Approximately 4000 to 400 centimeter inverse in the wave number correspond to the median infrared. And the infrared spectrum's absorption band may be related to the oscillation of specific valencies inside the polymer molecule or complete atomic groups, that is a functional group. Now, in light of this, infrared spectroscopy is an appropriate technique for examining the polymers and their additives. Now, using infrared spectroscopy, the qualitative and quantitative analysis is based on the wavelength dependent interaction on infrared rays with molecules or a group of molecules. Now, this interaction results in the generation of distinctive bands in the absorption spectrum, and IR spectroscopes, they are categorized based on how they choose wavelengths to analyze the light. The most popular one are the Fourier transform infrared and the dispersive IR spectroscope. This is the configuration diagram of an FTIR spectroscope. There are detectors, beam splitters, glober, flux mirror and moving mirror. So, this is the anatomy of FTIR spectroscopy. Now, in transmission reflection, the attenuated total reflection or ATR modes, the test specimen can be measured. This method can be applied to many films because the specimen thicknesses for transmission measurement range from 5 to 50 depending upon the IR transparency, and the signal from the specimen that are either too thin or too thick is too weak for analysis. The fillers and colorant can only be identified if one of the particle sizes is greater than the resolution limit, and the particles can be pushed into the FTIR microscope's measuring window. Along with the trans-illuminating the specimen, the material to be measured powder can be created under the nitrogen cooling and crushed with KBr or NaCl powder as IR ray neutral embedding substance. Now ATR or reflection spectroscopy are used to measure the specimen that are too thick or unsuitable for transmission measurements such as fiber reinforced plastic. An IR neutral optically highly reflective crystalline substance, that is diamond, is softly pressed onto the surface of ATR measurement. The total reflection can be seen at the edge layer at the right angle. Now, by using this technique, surfaces can be described without extensive preparation. Now, this particular figure displays the characteristic spectra from polymer or PELD that were produced using ATR. Now, different bands in the spectrum are that are also referred to as a fingerprint arise as a result of changes in chemical structure. Let's talk about the laser technology. When using light microscope tool on finely spherical semicrystalline polymer with particle size between 100 nm and 5 m, there are restrictions on how precisely one can determine size, shape, distribution and anisotropy. For a structural component ranging in the size of 100 to 10, these values can be determined using optical diffraction with a linearly polarized light, and the measurement is carried out using either separate optical laser light scattering apparatus or a light microscope with a laser or linear polarized light from strong commercial microscope illumination at a very small illumination aperture. Now, with the aid of an Amici Bertrand lens, scattering images that appear in the back lens focal plane can be captured on conoscopic beam path and afterward accession in a photometer using the microscope heating stage, and this method's extremely high optical resolution measurements may be made as the spherities are formed from melt. Additionally, it often opinion on growth and nucleation at different cooling gradient. Now, this is the you can see the light scattering phenomenon, various polymer structures like rods, different type of a disc, unstructured and scatters. So, this is the scheme of a scattering image under the creation of a different structure in polymer materials is shown in this particular figure. The advantage of using light microscope for a small angle light scattering is then it can capture the scatter and a micro photographic image of the specimen section that need to be examined. Now, this particular figure shows the structure of PEND and the corresponding scattering image. So, dear friends, in this particular segment, we conclude the polymer testing, and in this segment, we discussed about the optical testing, different form of optical testing in a more specific way, and for the convenience of the student, we enlisted various references which you can utilize as per requirement. Thank you very much.